Yeah. Oh. Okay. Okay. What is a polynomial function? Um, you guys should be able to recognize the polynomial function is simply a bunch of powers where the exponents are whole numbers. Okay, that's very important. So when you see this like this general thing happening here, like a sub n times x to the n power, a sub n is what we call the leading coefficient. And I call it the leading coefficient because it's next to the term with the highest exponents. So n we call the degree of the function. So it's all coming back to you guys. And that's the highest exponent. And the exponents are always whole numbers. So for a polynomial function, the exponents are always whole numbers. So no negatives, no decimals, just whole numbers. So technically the exponent could be zero. If it is, then guess what? You just have a constant, right? Like if you think about a sub zero, that's going to be our constant term. There's actually an x next to it, believe it or not. It just happens to be next to x raised to what power? X to the zero power. And we tend to write these in descending order. So if you have like a degree 4 function, you do x to the 4, x3, x2, x1, x0. So we want to be very orderly about this. The domain should be pretty obvious. What's the domain going to be here? All real numbers. Yep, there's no breaks in this graph. All real numbers. The range may not be, though. Depends on the end behavior. Also depends on high-low points, which is where the calculus comes into play. So you guys might have remember graphing these, and you weren't probably sure, like, hey, how high does it go? How low does it go? Now you will know. Now you will learn that because you use calculus pencil for that. Not today, not next week necessarily, but eventually you will, because we have to use calculus to understand how where the peaks and values are going to be for these graphs, and we call it the extrema, right? So we're going to be using calculus to help us find those things. But for the most part, just know that polynomial functions have exponents that are whole numbers, and you have a bunch of coefficients. A sub n is the leading coefficient, and your degree, your highest exponent. These are smooth curves. There's no sharp corners. It's very continuous, right? So that's the generality of polynomials. Does that make sense? All right, cool. So end behavior. Or sorry, before we do that, let's talk about what is a polynomial function. Which ones are? So again, it's got to be nice and smooth, no breaks, right? Domain's all real numbers. So of these four graphs, only one of them is a polynomial. Which one is it? Yep. That's no sharp corner. That's no. There's a discontinuity. We're also going to talk a lot about continuity in this unit. What does it mean for a graph to be continuous? And that's a big part of calculus. And likewise here, there's also a no, and that's also a discontinuity. What I mean by discontinuity is that if you took like a pencil or a pen and tried tracing the graph, if you ever have to lift the pen or pencil off the paper, you're not continuous. If I were to trace B or D, I'd totally have to lift my writing utensil off the paper, or if you're using a stylus, lift it off the screen, right? More specifically, we call this a jump discontinuity, and we call this an infinite discontinuity. So I'm also going to be very formal with the language too. I'm going to be using calculus terminology with you guys. Technically speaking, we do call this a vertical asymptote, as you guys have learned. But from a calculus perspective, we call it infinite discontinuity. Why do you think I would call this? So, I mean, I'll draw the dashed line. We know there's a dashed line there. In fact, there are two dashed lines. And usually you call this a horizontal asymptote because clearly it's a horizontal line, right? And we call this a vertical asymptote. Sorry, I was really missing handwriting. But the vertical asymptote, I like to actually call it infinite discontinuity. Why do you think I call the vertical asymptote infinite discontinuity?
Because it goes on forever.
Yes. See that arrow points up forever? Perfect. That's exactly it. And the arrow points down forever. So what's happening here is that as x gets closer to zero, what's happening to y on the right side of it? Is y is going towards positive infinity. Or what's happening to the left side? Y is going towards negative infinity. And we're going to talk about this from a limit perspective. We're going to talk heavily about limits in this unit during this month. Look at the horizontal asymptotes. So you see how it's getting closer to what y value. As I go further to the right or further to the left, what's y getting closer to? Zero, correct. So we call that a horizontal asymptote or y equals zero. But sometimes we also call it an end behavior asymptote. End behavior is probably a better way to call it. It's a little more general because you are looking at the ends of the graph. Because here's the thing. This may not be horizontal. Did Mr. Van talk about slant asymptotes to you guys? Okay, good. Awesome. We're going to see that. We're going to talk about that. That could happen. Or you may not. And also, why is it y equals zero? Why is it y equals some other number? Or why is it a slant? Sometimes they might even be parabolic. That could happen too. You get some really funky asymptotes. But we call it end behavior because you're looking at when x approaches positive infinity or x approaches negative infinity, what is y doing? How's y behaving? How's a function behaving, right? So this is all parts of the foundations of calculus we're going to talk about. Okay, so obviously I'm not going to do all these with you. I'm going to do maybe I'll do A and I'll do I'll do A and D. How about that? I'll do and then so we're going to skip around quite a bit here. So let's talk about end behavior. Okay, end behavior. The end behavior function refers to what's happening to the output as x approaches positive or negative infinity. So we're going to get used to this notation called limit notation. Has everyone ever seen this before? LIM? Kind of. Okay. Let me explain what this means. So the one thing about calculus is it's kind of a language. So you have to understand what all these, the notation. The notation can be a little funky. So when you see this here, I'm going to copy it again. So you, like, for example, if you take someone who's like a, I don't know, humanities major or someone who hasn't done math in a long time, they're going to look like, this just looks weird. Like, what the heck is they think are like super geeky about math, right? It's not that hard. I'll tell you what it means. Here's what it is in plain English. What does y approach when x approaches negative infinity? That's what the question is asking. Actually, I can't spell and I should put a question mark. Here we go. So that's what this means in plain English. When you see LIM, LIM is short for limits. When you see x arrow negative infinity, x approach negative infinity. When you see f of x, I want the limit of f of x, meaning I want to know what y is approaching. What is it getting closer to? And of course, what it equals. So that's what it means in plain English. Now, what is it? Is it easier to write it all in words or put it in the mathematical notation? Mathematical notation is easier, right? It's shorter, it's more compact. So that's why we have these notations so we can express what we want in a more efficient manner. So that's what it means. So graphically speaking, this means we're looking at um, the left end and right end. Because think about it. If x is going towards negative infinity, isn't that the left side of the graph? That's going towards positive infinity. Isn't that the right side of the graph? Right? That's all we're doing. So we're going to do this for part A, so you guys get the idea what's happening. Then we'll do again for part D. And then anything I skip over will be homework that you could do at the end of class or at home. So let's look at, so does that make sense? What's happening? And by the way, feel free to use graphing calculators for the stuff we do today. Feel free to use Desmos if you want to pull up your device. 100% is totally fine. Um, so let's take a look at part A here. Now you could graph this in Desmos. You can. I kind of know what's going to happen here. So I won't move the screen. We'll do this here. So we'll start with this one. You guys should know generally what y equals x cubed does. What does that do generally? It's like a snake, right? Okay. So with that said, what will be the limit of that graph as x approaches negative infinity? What is y approaching as x goes farther to the left? It's going down, so we say it's negative infinity. Does that make sense? If I'm going, so the left arrow, what is the left arrow doing? Is it pointing up or down? Down. So that means that y is going towards the infinity. So if I plug in like, say, for example, now see numerically what's happening. You see graphically. What if I plug in like negative 1,000? How many zeros is that when I cube negative 1,000? So 9 zeros, right? So negative 1 billion. So that's crazy. That's going really low. Okay, what if I plug in a large number for x, a positive number for x, like say 1,000? What's 1,000 cubed? 1,000 times 1,000 times 1,000. 1 billion. There's 9 zeros, right? So it's positive infinity. So we see it visually, we see it graphically, and we understand numerically what's happening. Okay, now we're going to look at it from a more algebraic perspective for the other function. Lucas, go ahead.
When you write like the signs of infinity or plus infinity.
Correct. Yes. I'm going to be a hard ass about it. Yes. You have to. Yeah. We have to be very detailed here at this point. Yeah. So, because, I'm preparing you guys for AP. So, yeah, we have to do that. And you can't get lazy about limits, by the way. When we start getting more deep with limits later in this month, you're not going to like it, but you have to constantly be writing these limit notations over and over again. I know it's not going to be fun, but we have to do it. Okay, let's look at part A. Sorry, let's look at the other function that's a little more involved. X cubed minus 2x squared minus x. Of course, x is still approaching positive negative infinity. Cool, fine. And you have negative 2x squared negative x. Here's the thing. If I plug in 1,000, right? We already know 1,000 cubes is a billion. What's 1,000 squared? 2 million. And then, of course, negative 1,000, right? Well, let's think about this in terms of currency or money, right? What if you have $1 billion and you have to give someone 2 million? Is that really going to put a dent in your wallet?
No.
No, if you have $1 billion, who cares? Give $2 million to like, Stanford or us. I don't know. If you give me 2 million, I can use it. Or if you give away $1,000, just drop in the bucket. Like, yeah, $1,000, here we go. And people do that here all the time. So these two pale in comparison to a billion, right? So here's the deal. Do these two terms really matter when it comes to end behavior? They're negligent. They're totally insignificant, right? So if it's going towards negative infinity, I'm cubing a negative number. Well, that's going to be negative. If I plug a positive infinity, like 1,000 or 10,000, whatever, that's still going to be, positive. So in this case, we expect the same thing to happen. You can graph if you want. I'll go to Desmos right now. We'll take a look at it.
Let's write the plus sign too.
If you don't do it for infinity, then it's implied it's positive. So you don't need to. But it's a good habit to do so. But if you don't, I'll assume positive. But if you want negative, you better put a negative though. But yeah, if I just do it really quick here, y equals x cubed minus 2x squared minus x. Like, big deal. Fine, there's some curves, whatever. Fine, I don't care. But still, the end behavior is the same. It does not change. So what is this? What's the moral of the story here? The end behavior depends on only two things. What are those two things it depends on? The leading coefficient. And Kingston, you mind close the door, please?
Yeah.
And whether it's positive or negative. And the degree, whether it's odd or even. And you guys remember talking about this in Mr. Band's class? Yeah, it's probably the first time we were introduced to that concept. The end behavior only depends on two things: the leading coefficient and the degree. If the degree is even, as you can imagine, if you square a negative or positive number, what do you do? It's the same thing, right? So the arrow is going to be in the same direction when it's even. And hopefully that makes sense. If it's even, arrow's in the same direction. But then the leading coefficient will tell you the direction. Are you both up or both down? If you're negative, like negative x squared, that's the parabola points down. Great. Both arrows are down. So negative infinity, negative infinity for your end behavior. If it's y equals x squared, great. Positive infinity for both left and right arrows. But what if you're odd? So if it helps, think about the arrows being at odds with each other, right? They're going opposite directions. So if you have an odd degree, like I have here for part A, they should be opposite because if you take a negative number, raise it to an odd power, it's negative. If you multiply a negative odd number of times, it's negative. But if you multiply a positive odd number of times, fine, it's still positive. But of course, it could switch direction if your leading coefficient is positive or negative. So like y equals x cubed, we have that. What if that y equals negative x cubed? It flips. So it's the other way around. So just be mindful about those two things. So it means there's four possible scenarios. Positive infinity, positive infinity, negative infinity, negative infinity, negative infinity, positive infinity, positive infinity, negative infinity. You don't have to memorize it, just understand numerically what's happening, and you're fine. Let's look at one more of these. I'll skip B and C because you guys can do it on your own. Um, okay, what's happening here? Okay, so y equals, okay, that's kind of crazy. Negative 2/3 x to the sixth power. I don't, I mean, I don't want to plug in numbers because I'm just getting kind of lazy, but I feel pretty confident the graph looks like that. Why do I feel confident about that? And the degree's even. So I'm gonna have this here. So guess what? I'm gonna have the same exact thing. Who cares? There's an x forward, negative 3x plus 1. Why? Doesn't matter. So if I do 1,000 raised to the sixth power, I mean that's just so many zeros. Now it's like Elon Musk money. No, he's a trillionaire. Well, he's almost a trillionaire, I think, but you know, he's kooky. Uh, okay, we're cool on that. And I apologize if anyone's friends with Elon Musk. No, just kidding. All right, okay, let's keep going. Um, so a sub n we know is the leading coefficient. So notice we didn't do B and C, so you'll just do that on your own. And I don't know if I have an answer key for this. I'll have to make one. And n's going to be the degree. If n is even, then you're up, up, or down, down. This is when a sub n is positive or a sub n is negative. If you're odd, arrows are at odds with each other. That's true if a sub n is positive or if a sub n is negative.
No one's like, boring, like, when I'm shedding around, I know all of that.
Okay. Any questions on end behavior? We good? Okay, power functions. So what is a power? This whole embodiment is called a power. So we say x to the a power or to the eighth. So if it was like a 10, we'd say 10th power, right? Or 20 to the 20th power. The x is the base and the a is the exponent. So let's make sure we're very clear on our language here. I'm pretty sure you guys are cool with that, but in case you were confused, x is the base because the bottom, a is the exponent's higher up. um, and I'm a little confused why I have to put in the blank there. One sec. K and A are, they're just constants. Not necessarily, because K could be negative. No. I have to be. Hmm. I mean, you can say non-zero. I don't know. I'm not sure. Let's just get rid. I'm not sure why there's a blank there. There are constants though. That I do know for sure. Yeah, I'm not sure why.
Same.
Yeah, but you can still technically call it a power function if you wanted to. You know what? We'll just go non-zero. I like what Emma said. We'll go non-zero. Okay. So now, are all, some, or no power functions considered to be polynomial functions? So it depends. To be a polynomial function, A has to be a whole number. Because you could technically have A be negative, in which case that'd be rational. Or if it's a fraction like 1/2, what if A were 1/2? What is that going to be called? Give A to the 1/2 power. Yeah, radical. Yep. You get radical functions too. Right. So that's a possibility. But if A were negative, it'd be rational if A is a fraction, it'd be like a radical. A fraction is not simplified to a whole number, mind you. So okay, we're good on this terminology and how these things are acting and behaving. Okay, cool. Um, I think I said a lot there. Sketching the graphs of power functions by hand. Ooh, that's a good one. Oh, these are fun. Okay. Yeah, these are really fun. Okay. I'll do part A, and we have you get then do part B for homework or whenever you get a chance to do it. So we're gonna draw each of these scenarios here. And I'll do red for Y1. We'll do blue for Y2. I'll do forest green for Y3. And we'll do black for Y4. Okay. And A represents the exponent, right? Remember, A is your exponent. So first one's pretty easy. What is that just gonna be? Yeah, it's just a line. That's all. How about for black was X squared?
So,
Yeah, not the best looking parabola. Do my best here. That's really crappy, but you get the idea. Actually, it's kind of bugging me. Let's do a little better. What? I'm kind of struggling, but that's all right. How about the other one? Yeah, so it's gonna look kind of like this. And how about the last one? Like a semi-parabola, but sideways. So where do they all pass through? 1, 1. And when k is positive, All four graphs that lie in the first quadrant exhibit the four possible shapes. Um, yeah, so this is so also we're assuming when k is positive, right? Um, but sometimes it could flip, right? That could happen. Um, when k is less than zero. Because you will flip. So you could have something in the second or third quadrant that could happen. Okay. So a question on that one. So I'll have you guys try part B later. Let's move on to page 5. Ooh, I gotta plug my laptop. Okay. Okay, let's talk about factors. That's important. And there's all these different terms you can use for solutions. So these, they could be called x-intercepts. They could be called a solution or a zero of the graph, or x minus a could be called um, the factor of the function. Whoa, what's going on here? Hold on a sec. Oh, thank God. All right, now we're good. Okay, cool. Okay, the polynomial degree n. Now this one part's kind of interesting. What if I had this here? So notice I made up a cubic function where my x-intercepts were what? 0, 1, and -1. So I have three x-intercepts, right? Um, how many extrema? Extrema mean like peaks and valleys or high points, low points. How many high low points does this graph have? Two. Yeah, there's one peak and one valley, right? So when you have a degree n for your function, you could have at most a local. The local means that it seems like it's the highest point for the time being. I mean, truly, do I know the absolute highest point of the graph? No. Sky's the limit, right? Do I know the absolute lowest point? No, because it goes down forever. But a polynomial function of degree n has at most how many local extrema? Well, clearly I count two, right? The degree is 3. If you were to expand that, x times x minus 1 times x plus 1, you have x cubed, right? I know it's going to be x cubed time plus a bunch of other junk. I don't feel like expanding it. It's not really necessary or relevant. But how many extrema I have? 2. So in general terms, you'll have at most n minus 1 local extrema and at most n real zeros. Granted, some of these zeros could repeat, and that's when we get bouncing. Graphs could bounce off the x-axis. Or you may not get n minus 1 local extrema. Like, for example, y equals x cubed. Y equals x cubed. Y equals x cubed looks like this. Are there any high points or low points here? There's zero extrema. This is always increasing. So you may get none. That's a possibility. And obviously this has one x-intercept. By the way, we talked about this when we did complex zeros, when we did De Moivre's theorem, all that fun stuff, right? Technically speaking, there are 3 complex zeros for x cubed, but only one real one because there's one x-intercept. The other two zeros are complex. We can't see them. They're imaginary, right? They're not there. But don't worry, imaginary don't really have much of a place in calculus. We don't really spend too much time talking about that. Yeah, sure, of course, yeah. So algebra determined the zeros of this function was the maximum local extrema that fx can have. Okay. Um, this should be pretty straightforward. What can you factor out? And you're stuck with what? Okay, and then I know there's always fancy ways of factoring. If you do trial and error, that's all good. I don't care. Getting kind of lucky here. I think I got it. Yeah, cool. Okay, so what are my zeros? 0, -1/3, and 2. What's the maximum number of local extrema it could have? 2. In fact, it does have 2. But sometimes they can repeat. If you have x minus a to the k power, where k is the number that's not 1, fine. It could repeat. So when it touches the x-axis, we're calling that a bounce. That happens when you're even. So there's no crossing. Where if it's odd, then it crosses. And the best way to tell, did you guys do something called interval testing or sign charts in Mr. Band's class? Yes?
Yeah.
Okay, we're gonna do a lot of that in this class. The sign chart is gonna be your best friend, especially as we get deeper into calculus. The sign chart is like a number line. So for example, if I did it for example 1, let's say I did a sign chart for example 1. So I'd have a number line down below, right? If I plug in, say, oh, let's plug in 1,000. 3 times 1,000 cubes. That's a pretty big number, right? That's 3 billion. But in -5 times 1,000 squared minus 2, who cares? You're still positive, right? In this interval, x larger than 2, what's happening to y? It's positive. You can plug in any number larger than 2, y is going to be positive. Now, let's plug in a number between 0 and 2. Give me a number between 0 and 2. If you plug in 1, what is y going to equal? For example 1. 3 minus 5 minus 2. So y is negative. When y is negative, are we above or below the x-axis? Below. So are you crossing the graph at x equals 2? Yes, you're going to break that graph. So you're going to break the x-axis. You're going to break through. Okay, 0, -1/3, -1/3, and 0. Well, it might be easier to plug into the factor form. I don't know if you plug in like -1/10. Kind of crazy, but if you plug in -1/10, that's -1/10. That's going to be 0.7, and that's going to be like -2.1. Where you multiply two negatives and a positive, that's positive. And last, if you plug in like say -1,000, you're gonna have a negative number. So we notice the signs alternate because every factor here have what exponents. I'm raising x to what power here? 1. I'm raising this factor to what power here? 1. This factor to the 1. If every factor occurs an odd number of times, you'll see an alternation in the signs, meaning you're going to be crossing the x-axis at each of those places. Because y has to change from positive to negative. You have to have that transition in a sign change of y. So we'll talk more about that when we get some examples.
Is how the chart shows you where it bounces and crosses.
So whenever the signs alternate, that's always gonna be a cross. Yeah, so yeah, I kind of glossed over that. So this graph we would expect to cross at each of these 3 locations. Because none of these factors occurred an even number of times. And the sign chart, which is just numerical analysis, proves that, right? Because if I plug in numbers in each interval, I'm noticing that y is going to be switching from positive to negative at every interval change. Now, what if I had an x minus 2 squared? Then I'm not going to see a sign change at this transition point. Meaning that, oh, if y stays positive before and after 2, that's going to be a bounce. Because we never have y be negative at that area. at that region. So sign charts are a really big piece of evidence to help us figure out these graphs. So let's actually do one right now. I won't do example 3. I'll do example 2 though. Again, while this is review, and this is where we'll start applying some calculus principles to this stuff next week. If I were to expand it, what would be my leading coefficient? And what would be my what would be my highest exponent? Good. Yeah, that's how it would look generally. So for part A, my degree is 5. For part B, my real zeros are going to be 2 and -3. For part C, the multiplicity. So x minus 2, how many x minus 2s do I have? So 2 will be twice, and -3 would be how many times? 3 times. Okay, the end behavior. We're going to write it like this. We're going to get in the habit of writing limits here. Okay. Well, you know your leading term. -5 times x raised to the 5th power. Your degree is odd. Your leading coefficient is negative. What do you expect the arrows to do?
Okay.
Hold. So what's the left arrow doing? Up, and the right arrow? Down. Good. Up, down. Good. Sorry, I just heard a lot of different things. So uh, we like that. And part F, I mean, we kind of know it's going to have at most 4 local extrema. So how would the graph look? Let me draw some tick marks here. The y-intercepts can be crazy. I'm not even bother applying that many tick marks. If I plug in 0, what would my y-intercept be? Kind of crazy, actually. Anyone know what the y-intercept would be? I want to do the mental math. No,
Yeah.
it's not too bad. Oh, what if you plug in 0 to x minus 2 squared? What do you get? I disagree. You're off by a factor of 3.
Well,
So what's -2 squared?
yeah.
So it's 4 times -5, which is -20. Then what's 0 plus 3 cubed? 27. So what happens when you do 20? Sorry, -20 times 27. -540, correct. Yeah. So it's not too bad when you just break it down. So it's way down here, right?
That accurate.
The tick marks?
Like,
Oh, no. No, not at all. No. So I know the end behavior has to look, and I know I have to cross the x-axis at these locations. And there's a bounce, and there's a cross. That's because when I do my sign chart, if I plug in a number larger than 2, what if I plug in 10? What's 10 minus 2 squared? That's positive or negative? And 10 plus 3 cubed, but then times -5, negative. So negative. And because there's the 2 comes from x minus 2, of course, right? And the x minus 2 has what exponent? Even or odd? The x minus 2 factor has what kind of has an even, right? There's no sign change there. There's zero sign change because if I plug in like 0, for example, well, I know it's negative if I plug in 0. If I plug in 1, fine, -1 squared is positive. 1 plus 3q is positive. -5, not okay. Well, it's okay. It doesn't matter. Negatives are fine, but that's still negative. And then it's gonna be positive here because if I put like negative like 5 or -10, I'm gonna get negative times a positive times a negative. So there's a sign change because whenever the factor has an odd exponent, you're gonna see a sign change. So graph will look like this. Cross, hit this here. Now, do I truly know the low point's a -540? I don't. So we can't tell the exact location of the extrema right now. But soon we will. And actually, that's not gonna have to later in the spring because I gotta teach you guys some derivative techniques. They'll be much later, but you will learn that eventually. Once we start learning derivatives, you will learn that. Um, Let's be about calculus. It kind of opens up your horizons. You can start seeing other things. So it's still a sketch. It's still a rough estimate, right? But at least you should know your x-intercepts and whether you bounce across and end behavior too, right? Those are the things I care about. So what I care about, x-intercepts, and behavior, and bounce slash cross. Okay, cool. Yeah, Kingston, go ahead.
The, like, draw it, like, when it crosses,
Mhm.
like that cross where it's a word hour, you need to draw it where it's like, slanted, like the.
You know, great question. Not right now. That's what we call concavity. We don't do that in this class. I wish we did. You'll do that in Ms. York's class. You'll do that in AP Calculus. We won't do that here because I don't kind of take you to that point. But you will eventually do that. You will learn that. Yeah, because ultimately you have to be able to do these with high precision. Just haven't learned the skills yet. But you will. You'll be able to do that. So we'll skip example 3. Um, Intermediate value theorem. I'm going to come back to that later in the month. So we'll skip that for now also. So we'll just say skip because we are going to talk about this later. So we'll skip that for now. Okay, do you guys remember polynomial division? Yes, kind of. Okay. It's kind of a pain. And do you guys do synthetic division?
Yeah.
Yes, okay. Yeah. Okay, well, I have a way that I think is kind of cool that I don't know if it's been taught. So I taught in regular algebra 2 this way. And gosh, there are a lot of division problems here. Okay. Well, we'll keep on trucking here. Doing great. Time. Okay. So let me show you a way I like to do this. Okay. So don't do it this way. You could do this. And you have to do like the long division process, right? Okay. I don't like it. I think we are in agreement. We both don't like it. Yeah, you don't like it. I don't like it. So here's what I do. CPM teaches it this way because I know you guys at CPM.
Oh, I was generic.
Yeah. I probably don't need that many boxes. I probably did too many. Yeah, I think I did too many. That's okay. Okay, so let me back up a little bit here so you guys understand what I'm doing. If I asked you to do this, what would you do? You FOIL. Yeah, first outside, inside, last, right? You do X times X. You do that, you do that, do that. Sometimes in middle school, if you came from our middle school, they probably taught you to do it this way. They call it tiles, right? Do you guys remember doing it this way also? Yeah. X times x squared, X times 1 is X times -2 is -2x. You guys see what I did? I multiplied whatever square I'm corresponding to. Like X and 1 corresponds to that square. 1 and -2 correspond to that square. X and 2 correspond to that square. And then when I have all this junk here, what do I do afterwards? I clean it up. Yeah, combine my terms, right? Yeah, totally. So you get x squared negative x minus 2, right? Well, what if I did this in reverse? What if I said, hey, I want to do this divided by x plus 1? Well, of course, the answer is x minus 2. Because wasn't x plus 1 times x minus 2 equal to that giant polynomial, the trinomial, right? So if I divided x squared minus x minus 2 by x plus 1, wouldn't I get back to x minus 2? I should. So if I do this in reverse, yes, exactly. That's what I'm trying to do here. So let's do it for this one here. So I took my divisor, right? I think I'm calling it the right thing, or divisor, whatever. But anyway, there's no x terms, so I put 0 as a placeholder. So x squared, 0x, and 1. What do I multiply the x squared to get the x cubed? X, good. Yeah. So I'll put an x here. Okay. Then I multiply x to each of these other terms here. 0x squared and 1x. I know it's kind of redundant to write 0x squared and 1x, but just for the sake of seeing the multiplication part, I'm doing that for now. Okay. Now here's what does get a little bit confusing. In the final outcome, right? So I'm dividing x squared plus 1 into this. I need a negative 3x squared. Notice in this box over here, remember we had like an x and a negative 2x, right? Remember we had that earlier? And what those two combine to? Negative x, right? So look over here on the negative 3x squared. Right now there's a 0x squared. What do you have to add to 0x squared to get the negative 3x squared? Negative 3x squared, of course, yeah. 100%. So guess what? I'm going to put negative 3x squared there. Just like I had over here in this diagonal. What do you multiply to x squared to get the negative 3x squared? Okay, cool. And that's going to be still 0 x and negative 3. Oh. Okay. So it's an x here. What times do we add x to 0x? Oh. Okay, so let's get negative 3. Did I say negative 3? Done. Done. X minus 3 is the answer. I don't need to waste my time with all that crazy long division crap. It's nicer this way. It's cleaner. This is called the box method. I like it way better than long. I don't teach long division anymore now. When I learned about the night I started doing CPM and Rig Algebra 2, it's like it was mind blowing. It's like this is the way to do it now. I don't do it any other way. Because what I wanted is I wanted this.
Last question.
No, I want this times this times this. So here, guys, here's really what's happening. What do you multiply to x squared? So let me write this out. This is really the whole essence of what I'm trying to do here. What do you want to multiply x squared plus 1 by to get to the numerator? That's what you're trying to do. What do you multiply to this to get to this? Because in essence, this is equaling something, right? it equals x minus 3 because guess what? X cubed minus 3. Sometimes we're not too present to this, but when we are present to it, it'll make sense. Because what does that equal? That equals x squared plus 1 times x minus 3. That numerator is a product of these two binomials. But it's not painfully obvious by looking at it. It looks really nasty first, and there's this nasty long division process. I think that's something BS. Don't do it anymore. Don't. Please. Do it this way. So that's what I would do. I think I should do this again so you guys can see this again. Let's do it again. I think you'll really appreciate once you see it again in action. Okay, here's what I'm gonna do. By the way, depending on the degree is how many columns I make. If I see a degree 5, I'll do 5 columns or 4 partitions. And depending on the degree of the denominator, if I see like 2 terms, I mean, of course, if you skip a term, put 0 as a placeholder, I'll put 2 rows here. Okay, this gets to be pretty fun. Technically, they call this in CPM, call it polydoku, like Sudoku. I don't play Sudoku. I play Wordle and connections, but anyway. What do you multiply? So take the leading term, put in the upper left corner. You have 2x plus 1. What do you multiply 2x get the 4x5? 2x to the 4 power. Perfect. So that becomes 2x4. Now, do you see an x4 in that numerator? So it's 0x4. What are you going to add 2x4 to get the 0x4?
Minus X.
Negative.
Negative. No. Hold on. I don't see an x4 here, right?
Yeah.
And I have a 2x4 inside the box. So what I'm going to put over here so that these two add to 0x4. I want these two to add to
Negative 2x4.
Good. Yes, they can read. Negative 2x4. Because right now, I'll insert it. There's a 0x4 right now. Okay. Now, what do you multiply 2x get to negative 2x4? Perfect. Okay. And so negative x cubed times 1 is negative x cubed. Okay. Coming back to my numerator. See negative x cubed. What do I combine with negative x cubed inside the box? Get the negative x cubed in the numerator. Well, what's negative x cubed plus 3x cubed? 2x cubed. I want negative x cubed. Good. It's okay. Yeah, I know. It's kind of crazy, but once you get the hang of it, you can go fast. Nothing. Exactly. So it'll be 0x cubed. So it'll be 0x squared. And that's 0x squared down here. Times 1. Okay. You want 2x squared. What do you add to 0x squared to get the 2x squared? 2x squared. Yeah. So what do you multiply 2x to 2x squared? X. So that's x. And lastly, you have negative x. That's an x. So what do you add to x to get the negative x? Negative x equal negative x. We do run into a slight little issue. I'll get there in a sec. Yeah. So that'll be -1. And that'll be -1. So what I'm going to do is going to add one more column. I'm going to have one more column. And you don't see a constant up here, right? So what do you add to -1 to get the 0? 1. So that's going to be your remainder. Because technically speaking, you're multiplying by 1 over 2x to get there. So what you do is you say the answer is 2x4 minus x cubed plus x minus 1 plus 1 over 2x plus 1. Because if you were to multiply all that junk by 2x plus 1 by the denominator, you will get the numerator. You will get that. And I will tell you right now, in AP calculus, you're going to have to do this kind of division. So so calculus is broken into two units or two, I guess, general topics. Differential calculus, which involves rates of change, derivatives. Integral calculus, which deals with net change. Integral calculus is the antiderivatives, the inverse of derivatives. When you start doing this antiderivative stuff in a year from now or whenever you do it, you're going to have to use this technique because some problems just can't be done unless you do this technique. So you need to know this technique really well. And that's my job. That's why it's called pre-calculus. I'm preparing you for that next level. So we're going to make sure we're practicing this. Now, how you can verify this, and maybe I haven't decided how this next test is going to go, but but you could verify this in Desmos. What you could do, go y equals divide, and what is it? 4x5. And my short-term memory sucks. X cubed plus 2x squared minus x over 2x plus 1. Okay, you get something wacky. Fine, whatever. Well, the quotient should be the same darn graph. If it's not, you made a mistake somewhere. Yep, same graph. They overlap each other. That's how you know you did this correctly. You could do the graphic calculator too, but it's a little bit of pain. It's easier doing Desmos. So yeah, that's what I do. Now you could do synthetic. Um, this process works for any kind of division problem. See, synthetic's limited. I can't do synthetic with 2x plus 1. I have to factor out that 2 first because it has to be in the form of x minus or x plus a number with a coefficient of 1 to do synthetic. So I'd have to deliberately pull 2 out and make it x plus 1 half and then divide all the terms up above by 2 before or after the synthetic. I can't do synthetic with a nonlinear factor, right? So synthetic's very limited. But in case you're curious how synthetic looks, it looks like this. Well, I mean, I know you guys know, you guys have done it before, but we'll just review really fast. If you want the synthetic, you guys like stuff like this? Yeah, and why do I put a 4 in the upper left corner? Yeah, that's the 0 of the denominator. Because you're assuming it's a 0 of the function. Because you're dividing by x minus 4. So you're actually, when you divide without realizing it, you're actually factoring. All this ever is factoring. It's just a glorified way of factoring. So and then you guys remember what to do up here? Yeah, in any term that gets skipped over, you have to put a 0 as a placeholder. There's no x. Okay, to get kickstart, you bring that 5 down. Do you guys remember what to do next? Then, and then, and then rinse and repeat. It's just a cycle you go through. Ugh, it's a little nasty. Okay, so 5x squared plus 14x. And how do you know if whether you did it right or wrong? Just go to Desmos or your graphic calculator, or you can just multiply the quotient by x minus 4. It's kind of a pain, but you could do that because it should get you back to the numerator. But this is a technique you are expected to do. Sometimes I do like synthetic if it's a simpler process like this as opposed to the box method. Sometimes I do like it. I won't do example. I'll let you guys do it on your own. But hopefully that review makes sense there. So what I just showed you for examples 5 and 6, do you guys prefer doing long division or do you like this new way I showed you? I won't be offended if you like long division. You like long division? That's fine. Hey, if you want long division, go for it. I just want to show you. If you want long division, go for it. I'm not going to hold it against you. I won't be offended, but I want to show you another way. So, yeah, I think I did say not to do long division, but you can if you want. I don't care.
There's some.
But since that can only be done when it's a binomial that's linear. Yeah. I'll skip example 9 as well. Okay, last part before we wrap things up for today. When the remainder is 0, whatever you divide by is going to be a factor. That's what it says. I don't need to do the proof, but essentially, like I say here is when remainder is 0, the denominator is a factor of the numerator. That's all it's saying. I don't need to prove to you anything. That's all it's saying. Which we know that's true, like for any number. Like if I have 120 divided by 4, what's 120 divided by 4? 30, right? No remainder. Is 4 a factor of 120? Sure, of course. Yeah, 100%. So how would I go about this here? Because you're assuming x plus 3 is a factor. So negative 3 is a 0 as you're told. Oh, wait one sec. I lied. I lied. You're doing this to evaluate. Sorry, my apologies. The remainder is f of negative 3. My apologies. Of course, if the remainder is 0, then it's a factor. Of course it is. So my apologies. So the remainder is going to be f of negative 3. And you guys know the process. Of course, if it's 0, then it's a factor. We know that. But if it's not, the remainder is going to be the output. That's called the remainder theorem. Does that make sense?
Yeah, it's just that the 3 is -3, and then that makes the 12 be 6 instead.
Oh, wait, did I make a 6 somewhere? Hold on. 3, -9, -5. Wait. Oh, shoot, you're right. Sorry about that. My apologies. Yes, thank you, Marie, for catching that. So it's 6, correct. I'm human. Okay. So let's try this again. 1/2. Now you are told it's 0. So you do expect 0 to be the remainder. That'll be the last thing we'll do for today. I'll have to pick this up Thursday. Bring the 2 down. 1, -14, -7, 20, 10, 0. So what does that become? And then you have to factor further or use quad form or complete the square. We'll stop there because we don't have time to finish that off today. Um, kind of misjudge how long this would take. I still need to review this with you. You know what? I'm not gonna give you guys any homework don't worry about this. We'll just pick this up. No homework. We'll pick this up on Thursday. I'm gonna have to go a little faster. I'm gonna skip some things on the later in these notes because we're not doing complex numbers because it has no place in calculus. So don't worry, no homework. Yeah, these guys back into things. Oh yeah, if you want to do the contest, yes. Yeah.